All right. Uh, we survived the first homework. It was controversial as expected. Um, Hopefully the volume is okay. I had some people help me out this morning. Okay, so we're trying to move back to well, our basic high level goal is to make things as normal as possible. Yeah.
Do you know when the answers will be released for the first homework?
We didn't finish last night, but we have a staff meeting right after this, so hopefully we'll.
Is that one of those things where the late deadline for like 1 day late is 24 hours after that release?
Yeah, I'll push it back accordingly. Normally it would be like I had originally set it to like Thursday at noon. Now it would be like Friday at noon or something. Hopefully there'll be plenty of time. Um, uh, but yeah, so the office hours are kind of moving to in person. You'll see the front page start to get updated. I have most of the TA's rooms, but not all of them yet. My office hours as well will be in person, and mine today were pushed back 1 hour because we're also doing a staff meeting in person. It got a little complicated. Okay, so let me review a little bit what was going on last week. So on Tuesday, we mostly focused on this problem subset sum, which was as defined, kind of a pretty simple looking problem. I'm just trying to add up some numbers to a target value, and in fact, we did have some kind of mixed success developing an algorithm. We got this n times t algorithm, which maybe for some cases when t is small is better than an exponential time algorithm. However, strictly speaking, in terms of getting a polynomial running time, in the input size, wasn't really a polynomial time algorithm. And in fact, we can take a SAP problem and encode it as a subset sum problem, which offers some explanation for why we couldn't quite get that very clean, truly polynomial running time. Okay. Now, by contrast, on Thursday, we looked at a few problems with more algorithmic success. So one of them was edit distance, which is just a very useful way to compare how different two strings are. We took really the same approach as we did to subset sum. We figured out how to kind of break it down into subproblems. We applied some caching, and out came a polynomial running time, m times n. Okay. So I think it's a little bit kind of surprising. I don't have a great answer to why edit distance turned out to be so much more tractable than subset sum. Right? It's kind of this big question of why. And if anything, if I didn't know anything ahead of time, I might have guessed that the edit distance would have been the harder of the two. In some ways, the definition of the problem seems more complicated than subset sum a priori. Okay, but it turned out the edit distance, we were able to break it down into a truly polynomial number of subproblems. Subset sum, we couldn't quite, although we got somewhat close. Okay, so it's a very interesting contrast. So today we're going to explore similar themes, but we'll start talking about graph problems. So graphs will really start entering the picture this week. We haven't done much with graphs, especially since we kind of skipped over circuit stat a couple of weeks ago. So I have three problems queued up. One is called maximum independent set. Another is called coloring vertices. And the last one is called dominating set. They're all like very simple problems to define, but they're all quite tricky, it turns out. Okay, so let's see what's up next. All right, so independent set problem. So my impression is that everyone's worked with graphs before. Today, everything is in undirected graphs. Okay, so they're just kind of symmetric connections between points or vertices. Okay. A set of vertices is independent if for any two vertices in my set, they're not connected by an edge. Okay, so they need to be, so these two vertices are not connected by an edge. They're independent from one another. Simple enough. And the problem is to find the maximum size set of independent vertices. You want to grab a lot of vertices, but they can't be neighbors to each other. Okay. All right, so I left this, thought I would ask, I thought I'd ask you guys, what might be the maximum size of an independent set in this graph? Maybe I can take a raise of hands. Anyone find an independent set of size? We'll start small. 3. 3, okay. All right. How about 4? Okay. How about 5? Okay. Did anyone get 6? So no one's raising their hands on 6. Oh, we have 1 6, 2 6s. Anyone get 7? Well, there's even a 7. Okay, how about 8? Is there an independent set of size 8? I see a head nod, but I don't know if that counts as I'm understanding or I see 8. Okay, the last hand raise I got was for 7. I don't know the answer. How did you get 7? If I may ask. Oh, you had 7, right? In the pink? Oh, no? Oh, okay, 6. A lot of people had 6. Does anyone want to point out which 6? All right, I'm just going to point at a vertex and then you tell me whether to put it in this set. Okay, I'll start from the top. How about this one? Should I put that in the independent set? I'm getting a fair number of head nods. How about this? This one we can't. Okay, let me eliminate the ones we can't right away. All right, how about this? Oh, I shouldn't have started. Okay, that's fine. That eliminates this one. How about this vertex in the middle? Oh, people don't want it. Okay, how about this vertex? I'm getting more head nods than shakes. This vertex. Oh, we can't. Sorry. Eliminate some of these. Okay. How about this one? Okay, mostly nods. That eliminates this. And I guess we might as well put in this. So we got 5. Oh. Okay, but someone got 6? Am I missing something? So this is an independent set of size 5. None of the vertices we circled are neighboring one another. Did anyone actually get 6 and can maybe make some changes for us? I don't know the answer. No. Okay, we'll just leave it at 5, and if someone can get 6, great. This is a relatively small example. Still seems a little bit tricky. We're not supremely confident that 5 is the best answer, for example. Okay, so that's the problem. Besides trying to find the maximum independent set size, we can do a decision version. Is there an independent set of size at least 5? And you can also do a weighted version. where I put weights on all the vertices, and the goal is to get the maximum weight independent set. Okay? So besides looking at general graphs, we're also going to look at a couple special cases of graphs and also see if, to what extent the problem changes or stays the same when I add some structure. So the first will be intervals, or sometimes called interval graph. So think of each interval as a vertex, and they're connected by an edge if they overlap. Okay, so an independent set is a set of non-overlapping intervals. Okay, and the question is this one as tricky as the previous one? Is the kind of thing we'll be asking. This is quite common when you, for example, do things like job scheduling, where each interval kind of maps to a duration of time being taken up on a machine. Okay? And then the other special case is trees, which is, of course, a special case of graphs. Trees have no cycles. Okay? And we'll also try to solve the independent set problem or see if it's hard on trees. Okay? All right, so I wanted to take a vote. So we have 3 different domains for independent set problem. For each one, it could turn out to be hard in the sense that a polynomial time algorithm would imply a polynomial time algorithm for SAT. Or it could be easy in the sense that we do have a polynomial time algorithm. Besides this, you have a third option that you are not going to vote. Okay, so I'll take that one first. Who is not going to vote? Okay, so 3 people, 5 people. I'm counting that for all 3 categories. All right, okay. Let's start with graphs. Who thinks the problem will turn out to be hard in graphs? Okay, I would say that's like 90%. And then who thinks we'll be able to come up with an algorithm? Very few percent. Maybe 2% or something. Okay, how about the case of intervals? So I want to get a maximum weight set of non-overlapping intervals. Who thinks it'll be hard? Okay, I would say that's like 20%. And then who thinks it'll be easy? We'll be able to conquer this problem. 80%. Most people are voting or being honest, not abstaining. Okay, lastly, trees. Who thinks trees will turn out to be hard? Okay, I would say that's like 35%. And then who thinks trees will turn out to be easy? That feels like at least 70%, which doesn't make sense. Okay. Good enough. Okay. Great. And I think it's interesting also to think about, how these contexts change the problem. It doesn't have to be independent set. There's basically all 3 of those problems I gave earlier can be interpreted on graphs or intervals or trees or other special cases. Okay. All right. Okay, so independent set. Here we go. What's next? Okay, so I guess I forgot to write down what the theorem or the result is. For graphs, it will turn out to be hard to do the independent set problem. Okay? So let's prove this. Okay. So as usual, to show that independent set ought to be tricky, one approach is to take a problem that we already know ought to be tricky and see if we can solve it using independent set. Okay, so we'll assume we have access to a black box that can solve independent set. To what effect can that be used to solve SAT is what we'll use. We could have used subset sum, we could have used other things. We'll use SAT. So this is a little bit funky because SAT, of course, is a kind of algebraic formula thingy. But the black box takes as input not a formula, but it takes as input a graph. It takes as input a graph and maybe returns the maximum size independent set, or yes or no if you also feed it a k and you ask it if there's an independent set of size k. So at a high level, I want to take a formula and somehow turn it into some graph based on this formula so that the size of the maximum independent set in this graph will somehow inform and tell us whether or not the formula was satisfiable. Okay. So we'll have to do some kind of creative thinking to figure out how to express kind of Boolean constraints in some kind of graphical manner. Okay. So a little bit more explicitly, we're going to build this graph so that the formula is satisfiable if and only if there is an independent set of size k for some value k that we are going to figure out. Okay. All right. Okay. So high-level construction will be as follows. I'm going to take variables and really symbols representing appearances in the formula, and they're going to sort of be mapped to vertices. And a high level, I'll draw, pictures are coming very soon, but clauses, let me make this a little bit simpler. Let me assume a 3-sat formula. It'll clean things up because there's only 3 for each one, but I think it'll be clear. It's not strictly necessary. Okay, so from the point of view of 3-sat, a clause with 3 variables, one of these conjunctions, is going to map to a triangle over the corresponding appearances. So let me explain. What we're going to do, so here will be 2 clauses, A or B or not C, not A or not C or D. Okay, and I've taken sort of each of those symbols appearing in a clause, and I've turned each one into a vertex. There's a vertex. Okay, so these are vertices. They're each kind of mapped to some literal appearing in our formula. Okay. Right. And the other thing we're going to do, and so the idea is going to be like, taking this variable and adding it to my independent set will be kind of like setting C to be false in the assignment. That will be the conceptual mapping. But that also means that I need to impose some rules to make sure that I'm not allowed to take both A and A bar, because I can't set A to be true and false. And that's why we'll also add an edge whenever we get these opposite literals. Okay. So at a high level, the vertices in my independent set should map to my assignments. Okay. My goal is sort of to take one vertex from every triangle, but I can't take A and A bar simultaneously because I can't set A equal to true and A equal to false. Okay. So hopefully it'll become more clear with an example. So there's a formula, a 3-side up on top. Sorry about the mic. And I've already drawn out the triangles for each clause. So for example, this clause, A or B or C, corresponds to that triangle there. Okay. So you can already see that the maximum independent set size is 4 because you can only take one from each triangle, okay, which equals the number of clauses. The only rule we have to encode is saying, you can't take A and A bar. So we'll draw an edge like this. I can't take D and D bar, so I'll draw an edge like that. Here's another A and A bar. Here's a D bar, B and B bar. So I'm just connecting those opposite pairs because I shouldn't be allowed to set a variable to be both true and false. Yeah? So in terms of independent set, right, each edge is saying you can't take both vertices. All right, so continuing on, there's another edge. What else am I missing? C and C bar. Did I get them all? Okay, I don't see any other edges I'm missing, but I might be. Okay, but at least I think the idea is clear, even if I'm missing an edge. Of course, a computer wouldn't make a mistake. Okay. So these M clauses become M triangles. I can only take at most one vertex from each triangle, of course, because they're all connected to each other. And I'm also no longer allowed to take vertices corresponding to opposite symbols. Okay. I'll briefly point out that this graph is not much bigger than the original formula size. Each vertex corresponds to some appearance of a symbol in the original formula, and there's some cross edges which maybe squares the size if it's fully connected. Question?
So I take it as when we say D bar or C bar, that is not exactly the negation of D and C. That is just another way to express D and C in another clause, right?
So take this D bar here. That was the D bar that represents this D bar. So the way I drew it is I think of each vertex as an appearance of a literal in my clause, which is only satisfied by setting D equal to false. Okay, so if I added this vertex to my independent set, and we're about to do this, but I would interpret that as saying D is equal to false, right? And it would check off that clause, and I would get one vertex from that triangle. Actually, maybe we can work it out. I'm not 100% sure if this is satisfiable. I hope it is. What would be the maximum size of an independent set in this example we drew? In particular, can we get 4? Yeah. It's no larger than 4, that's for sure, because each triangle we can only take one, because everyone in a triangle is connected to each other. So I guess my question, the claim, is that this formula is satisfiable if and only if we can find 4 vertices to add to our independent set. I should have thought this ahead, but I didn't, so I'm asking. Did anyone find 4? Do people find 3? 3? 4? We have one 4. Anyone else find 4? 2, 3, 4. Trickling in. Soon you'll all be peer pressured to find 4. All right, you tell me which 4. Yeah, yeah, or vertices, whatever. Yeah. Okay. So you said A equals true is good. Okay, so let me. So we'll take both of those, and then you said B is true. Okay. So this one we've already satisfied this triangle, and I can't take that B anymore, so I won't. But I am able to get a new triangle over here, and then C is true. Okay, it wasn't so hard. Yeah, D is, I guess D could be anything at this point. There's probably more than one satisfying assignment. Okay. All right, so that worked in one. That seemed to he worked in one direction, which he started with he saw a satisfying assignment, found the independent set. On the other hand, suppose you just looked at the triangles and found those four vertices. This one's telling you that you can set A to be true. You know that you're not taking any of the A equals false because there's an edge. This one's telling you that you can take B to be true, and you know that you're not taking any B equals falses anywhere else. Okay, so you can map an independent set that covers all the clauses to a satisfying assignment. Okay? Only if you get at least one vertex per triangle. Every time I get a vertex from that triangle, I'm satisfying the corresponding clause. Okay, so that's the whole idea then. Is that we can take a 3-SAT formula. I guess I didn't write a 3-SAT formula there. Build some kind of, yeah.
Wait, when you said four vertices earlier, that's just corresponding directly to the one vertex per triangle, right?
Right, so we will be looking for an independent set of size equal to the number of clauses. If I had 100 clauses instead of 4, I would be looking for an independent size of 100. Okay. Yeah.
Does that change if you were to consider something like 4-SAT or 5-SAT?
Sure. So there's what about 4-SAT? What about 5-SAT? What about 6-SAT? So there's two answers to this question. One is that we already know that we can take any SAT and turn it into 3-SAT. That's a hand-wavy answer. The other, though, if you wanted to do it directly, I can ask. If we were doing 4 vertices per clause instead of 3, how might I modify my construction? We can make a square. Okay, we can make a square. Oh, why did that erase? Oh, it's all connected? Okay, sorry. So that would be like a square. Okay. That's not quite right, but it's in the right direction. What's missing? Yeah. Okay. I wanted to make the whole 4 of them fully connected. Okay, so this is called a clique. Whenever you have a group of vertices where everyone's connected. Okay, so that will let you do 4-SAT, 5-SAT. It really didn't matter how many variables were in the clause. You just make a bigger, fully connected clique. 3-SAT was just so it's prettier to draw. Great. Okay, so that's kind of neat because it's saying that graphs can be very expressive too. Okay. All right. Okay, so all right, so that takes care of the graphical. Yeah.
How does the 3-SAT enforce that you cannot take 2 vertices from the same triangle?
Oh, sure. So how does 3-SAT enforce? Well, okay, so 3-SAT doesn't. You are allowed to set. Okay, so the question was, how does 3-SAT enforce that you can only take one vertex from each triangle? Okay, so there is a little subtlety here. Of course, you can set A equal true to true and B equal to true, right? Whereas in the 3-SAT, you can only take one of the vertices. Okay, but so the answer is it doesn't enforce it, but the other answer is that's okay. What I'm really interested in is whether or not I can use independent set to solve 3-SAT. Okay, I know that no matter what, I can only get one vertex from each clause. Okay, I can only get 1 point for each clause. So really the question is, can I satisfy m clauses, which is the same as can I get m points? And a triangle is saying you can only get 1 point per clause. You can only satisfy the clause once. Even if A is equal to true and B is equal to true, once A is equal to true, who cares about B equals true? So this way we can say if you got m points total, that means you got exactly 1 point from each clause, 1 point from each triangle. And thus you're satisfying all the clauses. If you didn't, you could have gotten 5 points from one clause and left another clause unsatisfied. So a little awkward because it's not exactly a one-to-one kind of logical mapping. Okay. All right, so that's, any more questions about the graph? That was a good question, yeah.
So with these graphs, we should kind of treat the lines where you're connecting like A to A naught in two different triangles differently than we would treat the lines like in the triangle itself. Because like if you're connecting A to A naught, that's because you can't have both of those at the same time. But like you could have A and B at the same time, right?
Yeah, so absolutely. Okay, so it is true that we started with triangles that are kind of disconnected. Once we add the edges, they're not necessarily, I mean, now you have an amorphous graph. I don't know if it's fair to call it triangles anymore, but it's just an interpretation. So the game we're playing is, how can I rig independent set to encode logic? And all independent set really lets me do is to say if I connect two vertices by an edge, I can't take both of them. So the triangle part per clause is encoding that you can only kind of get 1 point per clause because you can only satisfy a clause once. In that first clause, if A is equal to true and B equals to true, you only satisfy one clause. You don't satisfy two clauses. And then the edge between A and A bar is saying you can't be setting A equal to true and A equal to false, which is also a logical constraint for many Boolean satisfiable problems. Okay. Okay. Oh, more questions about graphs? Yeah.
So then if you scaled that up to say 4-sat, you would have to have like a fully connected square, right?
Exactly. So that's what I guess maybe the green is misleading, but this was an example of, yeah. More questions about graphs? It looks simple, but it's not. It's very clever. Yeah.
I'm not exactly sure, but if we have like n variables and we have a fully connected graph, doesn't that mean that we kind of have n factorial numbers of triangles?
That's absolutely true. So by the time I've added all these purple edges, there may be many more triangles, so to speak. So the triangles are just to motivate the construction in the sense that the way I thought of how to build this graph was to first start off with a triangle for each clause and then introduce edges, right? Of course, if I start introducing, well, this wouldn't exactly happen, but if I start introducing edges like this, now there's kind of more triangles out there, right? So I didn't exactly mean like triangles after the fact, but sort of triangles is kind of as we think of the construction, just to kind of personify it a little. Maybe I should mention that another kind of vocabulary word that'll be used to say describe just this part of the construction is sometimes they'll call it like a gadget. Okay, as another kind of wrapping a name around some conceptual piece. You'll see that a lot. Okay? First, gadget doesn't really mean anything in particular, but that's what people say. Okay, other questions? Yeah.
So I just want to clarify because I'm a little confused. So for this formula for 3-sat, A, B, and D being set to true make it satisfiable, and then leave off the simple one.
Okay.
Which would then you would circle A and B, which are independent. So do you only, even if multiple things in the clause gadget could be set to true, do you just for the sake of convenience only take 1 point per clause? Is that what you're saying?
That's right. So I could satisfy this one by setting A equal to true or B equal to true, but ultimately I can only choose one. So I just choose one. Either one would be fine. The key point though is that we'll be able to choose one from each triangle gadget, clause gadget. We'll be able to choose one from each of the clause, triangle, gadget things. And there won't be any of those purple cross conflicts because we won't, in a satisfying assignment, we won't be setting A equal to true and A equal to false. Yeah, so there's actually a little bit of subtlety in the fact that there's an independent set if and only if there's exactly m vertices in the maximum independent set. There's a pigeonhole argument there that kind of we didn't expand out and do slowly. More questions? Okay. Okay. All right, so much for graphs. So now we'll go to the interval graph. And for this, just to make it a little more interesting, we'll do the weighted version of the problem. So, maybe there's 10 and that's weight 2 or something like that. Okay. I just want to see what our voting was. So this was 20% hard, 80% easy. Okay. All right. Okay, so let's see if we can make an algorithm. And let's start with just the simplest brute force approach and work from there. Okay. So the first step then, as usual, if I'm going to do it recursively, is let me sort of define what my function is supposed to do. And we won't be too clever about it. It's almost tautological. I'll just say this function I want to implement, I want it to return the weight, say the maximum weight of any set of a subset of the set of intervals I. It's a big fat I to denote a family of intervals that's non-overlapping, that's independent. I'm just saying I want the answer for this set of intervals. So nothing too crazy. And so, since this, here's one way maybe to implement it. In the base case, if there's no intervals left, I'll just return 0. Okay. Otherwise, let's just pick an interval, see what happens if we take it, see what happens if we don't. Okay. So I guess if I don't take the interval, I'll just remove I from my big family of intervals and recurse. Okay. If I do take this interval I, then, well, first I should get some points for the weight of I. And then I need to recurse on, I'll remove all the intervals that overlap with it. Okay. So if this was I, and I wanted to see what happens when I take it, then that means I'm no longer allowed to take those 3 intervals, and I'll recurse on the remaining intervals. Okay, simple enough. All right, so that's all this code is doing. It's just trying I or not and updating the remaining intervals accordingly, returning the better of the 2 choices. Okay. All right, so this is going to be whatever exponential time. You're trying everything. So now here's the question that I actually wanted to pose to you guys. Can we make this faster If so, how? Even if you save answers here, it's still slow. There's kind of any subset of intervals could create a different problem. Sure.
The intervals are comparable, right? So you could just sort it if you in a comparison-based algorithm.
Yeah, so we do have endpoints. They are kind of on a line. Okay, so we could sort them. Any ideas? What are some ways to sort an interval, family of intervals? Sure.
Based on their weight.
Oh, based on their weight?
So that later on we can just use a greedy algorithm that always goes from the maximum weight to the minimum weight.
Okay, so um, okay, so maybe these things have weights. Uh, okay, so just first we should mention that the greedy algorithm might take the biggest, heaviest interval first, or maybe I should circle it, and then eliminate everything overlapping, and then take the next biggest one, eliminate everything that's overlapping, and so forth. I guess I should have given you a better counterexample. It'll work for this one, but it's not too hard to come up with something where that won't quite work. Now the other suggestion though is to sort nonetheless by weight, and then do this brute force algorithm where we try including it or trying not, right? But it's not clear to me that we avoid this problem of just having many possible subproblems. Partly because the weights don't have much to do with the incidence structure of the intervals. Yeah.
So then maybe we can sort by the number of overlaps of one node with other nodes, so that we tend to try to let those with the less overlap to be the independent interval.
Okay, so this is also a very natural idea. We can order them by overlap. I think that even if I told you that everyone overlapped with 10 other intervals, right? So it's like very wide and pretty thin. I think we would still have the same issue. I mean, because if everyone's 10, then there's not much ordering to by overlap. Okay, so things that won't necessarily work include sorting by weight, sorting by number of overlaps. What was the initial suggestion for sorting? What was your initial suggestion for sorting? Yeah.
It's comparison-based, so it would have to do with this, something with the starting point.
You can also use the endpoints. You can also use the endpoints. So let's try using the starting point. Okay. All right, so we're going to number these from left to right based on left endpoint. Okay. Hopefully that's 3, 4, 5, 6, 8, 9. Okay, so that's interval 1, interval 2, interval 3, and so forth. Okay. It's kind of nice because it's not a perfect order in the sense that, you could have nested intervals, but it is a little bit more of a sequential order, resembling a little bit more our success stories from last Thursday. ordering by weight or ordering by overlap doesn't have as much of a sequential feel. I think it's fair to say. Okay, so that's exactly right. I guess I'm supposed to number these. So we can spend n log n time initially to sort the intervals. Okay. So let's take that exact same brute force algorithm as before. And the only difference is that before I chose some interval arbitrarily. This one I'm going to try choosing the first interval. Okay. So there's no intervals return 0. Otherwise, I'm going to test out the first interval from left to right. Okay. So let me just show the whole code then. What happens if I hit that? Oh, that's not good. Okay. Note to self, cropping isn't so elegant. Okay, so if I wanted to look at the maximum weight independent set among all those that exclude the first interval, I'm just dropping that first interval. Okay. Otherwise, right, if I have my first interval, there's a whole bunch of intervals that intersect with it. And then there's sort of a first interval that comes after it ends. Okay, so what I want to do is I want to recurse on these intervals if I take the first one. Okay, so that's what we've tried to do here. We find the first index so that the left endpoint comes after the right endpoint of that first interval. So AI is bigger than B1. Okay, and then I add the weight of I1 and brute force over the rest. Okay, so this is only a slightly more specific version of exactly the same algorithm as before. Ultimately, I am just trying out one interval and doing brute force. Okay, the difference, though, is that I always choose the leftmost one. Okay. Now, I'll suggest that this can make a really big difference. In particular, if I do it this way, sort of, each of these recursive calls is defined by a set of remaining intervals, right? Some family of intervals that we're going to brute force over. But how many sort of different families of intervals can arise if I do it in this fashion? How many subproblems will we generate? Just n. So all our subproblems are going to look like this, right? It's going to be, if I took the first interval, optimize over the fourth interval on. There'll all be suffixes of our ordered list. Okay, so there's small change, and suddenly we only have n, or n plus 1 if you include the empty set, subproblems. Okay, so this is perfect for this dynamic programming caching trick, right? We'll set up a recursive spec. This is, I guess this is the maximum weight independent set over intervals I onwards. Okay. So now my subproblems are so small. I mean, a hint or sort of it's a good sign that I can very compactly express my subproblems. If you just give me that first interval left, that describes the whole subproblem. That sort of automatically tells you that there's only a few subproblems. And if we were to code it, it wouldn't be so tough. You know, if I is bigger than n, if I is bigger than n, there's no intervals left. So we just return 0. Otherwise, we'll take the maximum of omitting that interval. So this is where we skip the ith interval. Or, one sec, I'll write this in a moment. We'll figure out the first interval that's bigger and add the weight of I. So this means we include the weight of I sub I. So what is j? J is the index of the first interval disjoint from I sub I. Okay, so the code itself is not too crazy. We can loop over and find that first interval. Okay, oops, sorry. All right, so how long will this algorithm take? So it's roughly the number of subproblems times the amount of time per subproblem. Okay. So how many subproblems would I get? We already answered that, but it was n. And how long would it take to do each subproblem? Maybe the code as written is a little deceiving because it's a little compact. Yeah. Oh, then, because I need to find j and scan through the intervals. Okay. So we get an upper bound of n squared for this problem. So it turned out to be easy. Congratulations to 80%. Now, okay. Can anyone do a little bit better? N squared is always already great. I mean, it's much better than what we could do on graphs. Anyone improve the algorithm a little bit? Yeah.
If we include caching, we can record which intervals intersect with each other, so we don't have to scan the whole list every time.
Okay, so I can try to calculate all the intersections, but there could be up to n squared intersections. So at least if I wrote them down all explicitly, that won't necessarily save me time. However, it's a good idea. It's on the right path. The suggestion was to record all the intersections or something like this ahead of time. So the bottleneck I want to address is not in the number of subproblems, that'll stay the same. I would like to improve the running time for each subproblem. Yeah.
We're finding like the first index that is after the B, then you could instead use like a binary search on J, and that would be
Yeah, so this is, again, this is the first index where the left endpoint comes after the right endpoint. So we can do a binary search among the left endpoints where I use B1 as a key, or I use the right endpoint as a key and figure out by searching the first interval that comes after. They're already sorted by left endpoint, right? We say we put in an array. Okay. So n squared's already great. If I add just a binary search to find the next interval quickly, then I only need to spend log n time to find the next interval. That means that this will become log n, and we'll get n log n overall. Okay. And I'll also note on the side that we did sort at the beginning, which also gives an n log n. This is still n log n. Yeah.
Can you explain why the number of subproblem is n?
Sure. Well, each subproblem is encoded by an index I between 1 and n. In particular, right? Maximum weight independent set of intervals number 5 is the maximum weight independent set, or the weight of it, over I5, I6, I7 down to IN. Okay, so there's only n suffixes of our ordered list of intervals. The key point was that we ordered at the beginning, we found a little bit more structure. The number of subproblems becomes just n. That's the biggest idea. Other questions? Okay. All right, so much for intervals. Now let's, our third case was trees. Okay. So we want to compute the independent, maximum weight independent set in a tree. And at some level, we're kind of asking, are trees just as general as graphs? Are they as simple as intervals? Right? Intervals we can do as fast as sorting. That's pretty good. Okay. And if I remember correctly, obviously I didn't count correctly, but this was a little bit more controversial. We had 30% who thought it would look more like graphs. No, I think I said 35. And 70% that said it would look more like intervals. It would turn out to be tractable. Okay. All right. Okay. So let's at least try to come up with an algorithm and see where that takes us. Okay. So if I did want to model this problem recursively, sort of there's a question of how am I going to order my subproblems? Okay. Now, so the question is, how can I impose some order on a tree? Any ideas? One can try to do topological order. Topological ordering is more natural for directed graphs. Maybe we can impose a direction into a topological order. In the back? Okay. Okay, so first of all, always a good idea is to just add the word sub in front and see how far that gets you. So subtrees, is maybe a natural way to break down a problem on trees. Okay. Now, one thing that maybe would help to set up subtrees, at some level as drawn here, I don't know, there's a couple different subtrees, but to make our thinking a little bit clearer when we want to do subtree stuff, let's just fix an arbitrary root. Okay, and then I can kind of think of the tree going down away from the root. That'll make it easier to think. So if I pick this root here, so let's do this. So if I pick this root here, then maybe, and I want to think of it as the root of a tree, we can try kind of messing around with this. This is like the peak of this class. Okay. All right, so that didn't work. Okay, so if I redraw it like this, why? Okay. So if I redraw it like this, right? Of course, this is the same graph, but now you do see a little bit more of the kind of subtree that maybe you imagine when you use the word subtree. Okay, so sort of similar in spirit to how we sorted the intervals, we found more order. We've rooted it, kind of fixed the top. Now we have a strong sense of top to bottom. Okay, that's step one. All right, so let's set up a recursive algorithm. Here's the spec. Again, it's almost tautological, but the point is that we're focusing on subtrees. A subtree will be defined by the root of the subtree. Now that the tree is rooted, that's well defined. Before, when it's sprawling, it's not clear who's the captain of a subtree. Okay, but now that it's rooted, I can use that top vertex as a representative of the subtree. Okay, so we've defined MWIS of V to be whatever the maximum weight of any independent set in that subtree. Okay, same as always. All right, so let's try to implement this. Okay, so I'm looking at some vertex V, and we're just doing brute force, nothing too clever. So I can either include it, or I can not include it. So if I don't include V, then I would just figure out what's the best thing here, what's the best thing there, and combine it. Okay. All right, it's the sum. Okay. Now, what if I wanted to include V? Okay. I wanted to try putting V into the independent set. Okay. So I would want to add up the weight of V, right? Because I've added it to my independent set. And then I want to somehow recurse over all the children, yeah.
To these children.
Yeah, so the issue is, if I just recursed over this and said, find the best independent set, the best independent set might include the root, right? And that would be violating that edge. Okay, so just putting MWISX here doesn't quite work. Yeah.
I mean, we can just introduce a new parameter. So it's like if we choose to exclude the root, then we're just, I mean, if we choose to include the root, then we're just going to exclude the root next time.
Perfect. That's, I think, verbatim. Okay, so when I'm doing that subcall, now, so another way is you can kind of dig deeper directly. So there's more than one way about it. I think this way will be a little bit more slick. But, when I was doing that recursive subcall, I didn't want the maximum weight independent set rooted at that child. I really wanted the maximum weighted independent set among those that exclude that child X. Yeah, question.
Okay, so what you said a minute ago, wouldn't that be MWIS X over children X of children of V? Since we're skipping all of that.
So this is wrong. Yeah. So you could try to do grandchildren, but we're going to do it a little different. Yeah. Okay. So the approach I'm going to take is, was there a question?
Okay, so I was just wondering if you could take instead add the weight of V. If you're including V, you could add the weight of V plus the sum of if X is a child of V, you could take the sum of all of X's children for each.
Yes.
So you could take like the grandchildren of V instead of the children of V.
Yes. So that would be correct if I wrote grandchildren. Okay. That's one approach. Let me give you a slightly second approach that's a little bit more top-down. And it'll be a little bit easier to calculate the running time at the end because it's sort of a pain to sum over grandchildren and stuff like that. Okay. So conceptually, though, the real issue was that my recursive call, one issue was that my recursive call to MWIS doesn't really give me exactly what I want. What I want is the best independent set that excludes that child. Okay. If I didn't want to hack into the grandchildren stage. Okay. So the other way to do it, instead of kind of going down a level, which would require some careful coding, is the lazy thing is just to add a flag to expand the definition of our recursive function. Okay. So now we have MWIS V and some flag that I called exclude root, because I was taught to give meaningful variable names. Okay. So if this flag is true, then I want the maximum weighted independent set among those that exclude the root. If it's false, it's allowed to include the root. May or may not. Okay. And now, in the interest of time, I'll just uncrop it. Now that we have the right definition, a stronger definition of MWIS, okay, so what we've really done is we have a much more useful induction hypothesis. Okay, now the subproblems are more useful. I just expanded definition. And even though MWIS X V, exclude root to some extent does more, it's actually much easier to implement now, right? If I have to exclude the root, there's no choice to make. So I'll just sum over the children, and the children can or cannot include the root. That would be the grandchildren if you kind of inline what's going on, right? Otherwise, I can either not include V, and then sum over the children. The children don't have to exclude themselves. Or if I include V, then I'll pass true to the subproblem because the children can't put themselves in the independent set. Okay, so by expanding out the specification, it actually became easier to implement the whole thing. Okay, so I want to make 2 points. One concerns running time, and 2, I only need to briefly introduce what coloring is because there's some PSO problems about it. Okay, so let's do this quickly. How many subproblems are there if I did this subtree approach? Just shout. N. And how much time per subproblem? N. Okay, that would give n squared. The reason he said n was because there could be n children. Right? Okay, but that's very conservative because adding up the total number of children over all nodes adds up to n. Okay, so we're more than double counting these children. Okay, So a slightly better running time. This time we have to be a little bit more sophisticated than our usual upper bound. What I really want to do is sum up the time for each problem, right? This is proportional to, for each node, number of children of that node plus a constant. Okay. If we sum all of that up, we get the total number of children, and that's big O of n. Okay? So graph, you can actually do in n time, in linear time. So it's actually faster, even easier than intervals, it turns out. You don't even have to sort. Okay? All right, so let me just go over this definition to set up the PSO a little bit. So the problem that we didn't discuss in detail is called k-coloring. Okay? The goal is to take this set of vertices and color it with as few colors as possible so that no two adjacent vertices have the same color. Okay? So as long as vertices are independent, they can have the same color. But if they're adjacent, they have to have different colors. Okay? Probably no time to finish this coloring, but you get the idea. Okay? So this problem does turn out to be hard. There's some nice pictures about it. Okay? And I'll also point out, and then you can think about also the problem for intervals and trees. That's what the PSO asks. And there's a slightly more refined version of the problem that will also come up on the PSO that's useful for the hardness reduction. It's called subset K coloring. So the goal is still to color the vertices in at most K colors, except for each vertex, I give you a list of colors that you're allowed to use for that vertex. Okay, so this is saying that this vertex can only use color 1 and color 2, I guess, out of 3. Okay, so that's slightly harder than coloring, and the PSO is going to ask you to think about how to do this problem on trees and intervals as well. Okay, all right, thank you.